Okay, let's continue beam column with end moment. Last lecture we studied beam column with transverse loading, right? Today I'll go through beam column with this end moment. Let's look at this. If you consider this kind of building, look at this member. This member has this kind of axial force and end moment here. If you take out this element here, then we can draw like axial force and then end moment, MA and B. Let's assume the clockwise moment. Regarding this beam column, let's drive amplification factor second order moment. Then take out this part to make the free body diagram. From this figure, your reaction here is MA MB over L. It is downward. You have the axial force here, you have internal moment here. So if you consider the external moment here, M external equal MA PY minus MA MB over L X, right? That is external moment. Internal moment is M internal equal minus EI Y2 prime. So external moment and internal moment must be identical. Then you can get this equation. You can also directly get this equation without the calculate external and internal moment separately. You just take moment here, then you can get this equation. And then divide by EI. And if you let k square equal p over ei, then you have this equation. So from left hand side, you can get homogeneous solution. And right hand side, you can get the particular solution like that. Now you have two unknown, a and b. So you need two equation, y0 equal 0, right? yl equal 0. Okay, diffraction, both ends are 0. From this equation, you can get A and B, this A and B. And then you can write the general solution. It is the second order diffraction equation, right? So A is this one, B is this one, right? Okay, let's calculate the maximum moment. You have to know the location of maximum moment. How to know that location? The shear force is equal to 0 at maximum moment location. What is shear force? EI Y 3 prime is shear force, right? Equal to 0. From this equation, you take the derivative 3 times, 1 prime, 2 prime, 3 times, and then equal to 0. Then you can get this relationship. Tangent kx bar equal this one. X bar means the location of shear force is 0. That means maximum moment location. We have this relationship. If you write like that, this is kx bar. This angle is kx bar, right? Minus ma sine kl. This term, right? And this term is here. ma cosine kl plus mp. So from this relationship, you can get and sine kx bar. Sine kx bar is this distance and this distance, the ratio, right? This distance is the square root to this term plus this term, right? Then you can get this one. So this one and the ratio over here, right? That is the sine. This one is like that. Cosine equal this one and the ratio of this one. That is relationship regarding the maximum moment location. Now we find out the maximum moment location, x bar, right? So let's calculate maximum moment. So maximum moment equal minus EI Y2 prime x bar. That is maximum moment location. EI Y2 prime is moment. From this equation, you can take the second derivative and then input the x bar instead of x. Then finally, you can get this equation. This equation and this one. Okay. So if you calculate this one, this square root to this term, square root to this term, and then you have to multiply sine KL here. So MA square sine square KL, and then if you calculate this one, then ultimately you can get here MA square cosine square KL plus 2 MA MB cosine KL plus MB square. Then ultimately you can get this result. So this term is deleted, the term in the nominator term. So remaining nominator is this one. So let's assume MB is greater than MA. This equation, MB is greater than MA. This equation can be rewritten minus MB square root to MA over MB, because we take out MB here, then we have to again divide by MB square here, right? So this is MB square divided by the MB, then 2 MAMB, right? Divided by MB square, then 1. Okay, so this equation can be rewritten as this, right? And then this is minus MB amplification factor. So then minus means so upside. Upside is tension based on this figure. Upside is tension, that is minus. By the way, second order maximum moment can be written minus MB AF. AF is this one, amplification factor. Then what is maximum first order moment in this equation? Can you answer me? What is maximum first order moment in this equation? That is MB. This is amplification factor. So and maximum is maximum second order moment. From here, the X bar, what is X bar? Maximum moment location. If you calculate X bar is greater than 0 and less than L, that means maximum moment occur within this member, like that. Okay, M maximum here, MB here, like that. But if you calculate X bar is less than 0 or greater than L, then maximum moment location is somewhere here or somewhere here. Okay, that means outside of this member. If you draw like that, maximum moment location is outside of this member. Then in real situation, what is the M maximum here? That is the boundary is within this member. So maximum moment is MB. If X bar is less than 0 or X bar is greater than L, that means X bar is outside. That means the maximum moment of this member is just MB. So far, we investigate the case of double curvature bending. The bending like that, so it is, we call it double curvature. But if the moment apply like that, counterclockwise, in terms of MB, counterclockwise, MA is clockwise, then deflection like that. So we call it single curvature bending. Let's look at the case of single curvature bending. So MB, the sign should be changed, right? So MB should be minus MB for single curvature bending, right? So M maximum equal MB and this amplification factor. From this equation, you use minus MB for single curvature bending, then minus minus plus. This term is identical. So M maximum equal MB and amplification factor. In that case, the maximum moment location tangent kx bar should be minus MB, right? Instead of MB. If you see here, double curvature case, that is the maximum moment, the location in terms of tangent kx bar, that is plus MB. Okay? Single curvature case, minus MB, okay, instead of MB, because the sign should be changed. So here, minus MB. It is only difference regarding the maximum moment location. Then let's draw this MA and MB. That is the first order moment. If we ignore the axial force in this beam column, we can draw the moment diagram like that. Okay, I think you draw many times in undergraduate courses, right? But there is axial force, so we have the second order moment here. That is M maximum here. If your calculate X bar is within in this member, that means greater than 0, less than L, then your M maximum exists within this member. And then N maximum must greater than MB, somewhere here. If your calculate X bar is less than 0 or greater than L, that means maximum moment location is outside of this member, somewhere here. Then what is the second order maximum moment of this beam column? That is MB, because this M maximum point here is outside, so we cannot consider it the maximum moment of this beam column. And then let's look at the combined equation like that. So if MA over MB is positive in double curvature bending, that means positive. MA, MB is negative in single curvature bending. Here, MA, MB is negative for single curvature bending. If you see here, negative, okay, for single curvature bending. Previously, in double curvature bending, it is plus, right? If you see, that is plus. This one is double curvature bending. Single curvature bending is minus. These two equations can be combined like that. Okay? Maximum moment, maximum moment. So the reason we take the absolute value here, we are just focusing on the magnitude absolute value. In order to get the maximum moment, you have to calculate the maximum moment location X bar using this equation. So it takes time, and then it is not convenient to calculate maximum moment. In order to get the maximum moment easily, we introduce the equivalent moment concept here. As I mentioned, if X bar is greater than 0, less than L, then maximum moment can be obtained from the equation. If X bar equals less than 0, X bar equals greater than L, this is not 5, L, this is L, then M maximum equal MB. Okay, so we have to calculate the maximum moment location before determine M maximum moment. Okay, so we would like to skip this procedure for simplicity. So we introduce the concept of equivalent moment. Okay, see here, this is some single curvature bending case, right? MA, MB, P of P. And then we consider M equivalent moment. Left hand side, generally MA and MB, two moments are different. Magnitude of two moments, MA and MB, are different. But we apply the same M equivalent moment. What is equivalent? Yeah, look at this figure. MA here, MB here, maximum moment somewhere here. Then we apply the same moment at both ends. The maximum moment must be identical. We determine M equivalent providing the same M maximum. That is M equivalent. This moment identical. In order to make this moment identical to this left hand side, we determine M equivalent. Yeah, that is the concept of M equivalent. Then that is the maximum second order moment, M maximum, right? From this condition. How about this one? M equivalent to the same both end moment, right? Then here MA, MB, same, so this is 1, right? MA, MB, M equivalent, same, this is 1. So 1, 2 cosine K, 1, right? But this is a single curvature. MA, MB sine must be minus. If we use this equation, we can write this equation for this specific case. So 2, 1 minus cosine K, okay? From this equation, we can calculate M equivalent. M equivalent. So this one and this one can be deleted, and then this term can be moved to left hand side. Then M equivalent can be written as this, right? Here MB is first order moment, right? This one is, it is called CM. This CM is equivalent moment factor. If you see this figure again, this is MB. In order to produce the same moment with this one, we have to determine M equivalent. That M equivalent equation like that. MB times this one. This one is called CM, equivalent moment factor. We multiply equivalent moment factor MB, then we can get M equivalent to make the identical maximum moment. In fact, CM is a function of, as you see, MA, MB, right? And what? Also P. CM is a function of P. If you see here, there is no P. Why? It is the function of P. Do you know why? There is no P here. Anybody can answer? This K, what is K? This K is square root 2 P over EI. So this K include P. So this PM is basically the function of MA, MB, and P. So Massonet and Austin, they suggested the design equation. This is some analytical equation, so the accurate equation, but it is difficult to use for designers. So Massonet suggested the equivalent moment factor CM. He just ignore P effect. He suggests just the function of MAMB. Austin also suggests another equation. Okay, if you see the figure here, that is rho. Rho is rho times P Euler Bucking load equal P. Okay, so rho means P over PE. If the ratio is 0.2, that is theoretical value. If rho equals 0.4, that means the axial force increase, then this line. 0.6, this line. 0.8, this line. That is theoretical curve. But the Massonet suggests this line. Okay. Austin suggests this line. Okay. This part is single curvature. This part is double curvature. Let's look at the maximum moment. If you see again, that is maximum moment, right? Using the equivalent moment, maximum moment. So you just calculate M equivalent is this one, CMMB. So maximum moment is M equivalent square root to this term. Do you know the relationship of this? 1 minus cosine KL equal 2 sine square KL over 2. Okay. Sine square KL equal 4 sine square KL over 2 cosine square KL over 2. You might know this equation you have learned from high school. If you use the relationship instead of 1 minus cosine KL, use this one. And then sine KL, you use this term. Then this maximum moment can be written simply. M equivalent is secant KL over 2. Okay? Secant KL over 2 can be written 1 over 1 minus P over PE. Then what is M equivalent? M equivalent is CM MB. This term, this is the first order moment. This is the second order moment, the maximum moment. So this term must be amplification factor. It is a design equation used in LRFT. So if you calculate amplification factor is greater than 1, your maximum moment is amplification factor times MB. If you calculate amplification factor is less than 1, then maximum moment must be MB. Do you understand? So maximum moment cannot become the smaller than first order moment. So if your calculate amplification is less than 1, then you just ignore this one. Then maximum moment is MB. So far, we studied the beam column subjected to axial force and end moment. So we have derived the maximum moment equation, and then we also investigate the amplification factor for that case, right? And let's look at some of the simple issue, superposition of solution. If you recall some undergraduate study, I believe you learned some superposition. Superposition also works at our stability problem. So, but in order to satisfy superposition, P must be constant here. Let's look at this one. This beam has some lateral load Q1 and Q2, and then P. Then this one can be divided into two. This figure, Q1 applied here and Q2 applied here. This figure is equal to this one plus this one. That is a superposition. In order to satisfy this superposition, P must be constant. As long as P is constant, Q, Y relationship is linear. If Q is constant and then P increase, then P, Y relationship is nonlinear. So superposition does not work. If P changes, then superposition does not work because P-Y relationship is nonlinear. I'll show you some example here. Then you might understand. Yeah, this beam subjected to distributed loading and then concentrate loading at mid length. And then we have to calculate the deflection from this lateral load and then axial force. You don't have any solution in this case because this beam is subjected to distributed load and concentrate load together. You don't have any solution. You have to derive by yourself using differential equation. But if you use the superposition theory, then you could divide into two like that. This beam subjected to distributed loading, subjected to concentrate loading. So this is YW, this is YQ. P is constant, not change it. Then this Y equal to YW and YQ. So you know YW. We already derived, right? So you know this value. You know this value, this two value before we have the solution. Then you just add together. Then you get the second order deflection. How about the maximum moment? You know the maximum moment in the case, right? Is this one. We already derived before. You also know the maximum moment in the case, right? The maximum moment in the case, you can just add this two by superposition. As you see here, if W increase, here W increase, moment increase. The relationship is linear, right? W moment is linear. And then here Q increase, the moment again increase, right? That is the relationship is linear between Q and M. So as long as P is constant, this superposition works. But where is P in this equation? U. U include P, right? So as you see, P increase, moment also increase, but it is linearly increase? No, because secant U, it is not linear anymore. Tangent U over U, it is not linear anymore. So if P change, the superposition does not work. But if P is identical, this kind of superposition, YW plus YQ or MW plus MQ works. From this some concept, we can calculate determine fixed end moment. Here, that fixed end beam subjected to lateral load and then axial force. So we can divide by into two, lateral load and then P applied, and then fixed end moment applied and P, like that. So we would like to determine fixed end moment. So superposition works here because P is constant. As you see, the beam column at both ends, the slope equal 0. That means the slope due to W and slope due to fixed end moment must be identical. So you have the solution, the slope here, Y prime W equal this one. Okay, second order slope. By fixed end moment, we have the solution also. Okay, because we already derived these cases. So this is slope must be identical. This one and this one should be identical. From that on, you can get MFA, the fixed end moment by superposition theory. Okay, let's finish this lecture. Bye, everybody.